At this point of the course, we found it helpful to introduce a brief logarithm review. Most students tend to be comfortable with exponential functions, but seem a little less certain when it comes to logarithms, at least on average. If you feel comfortable with them, that's fantastic. This should be just a very quick recapitulation of what you already know. It's often easiest to understand logs in the context of the relationship to exponentials because they have that inverse relationship. For example, if we have a base a and raise it to some power c and get a new number, the way to look at that with logarithms is to treat the logarithm as asking the question, what power or exponent is needed? That's the way some people think of the logarithm. What power of a do we need to get x? Well, the answer to that is c. What power of a do we need to get x is also c in this way of writing it out as well. Whichever way you want to think about that, these two forms are equivalent relationships between the three players, a, x, and c, the base, the exponent, and the value. Let's apply that through a couple of examples. Let's call this part here x and c. The equivalent notation then would be that we're taking a logarithm base a, so a to some power c, is going to give us x. But we actually had a particular x in mind here, a particular value inside that logarithm, and it's a to the 7. Well, what power should we raise a to get a to the 7? Pretty sure we should use 7 as well for the power on the left-hand side. And so log base a of a to the 7 is going to be that 7 value. In the second example, what we can do is recognize that we basically have this form here, a to the power c equals x. Let's give the log base a of 25 a name, and let's call it c to match the term up here. If we define this relationship, then what we can also say is that, well, we actually have this relationship now for a moment. Log base a of something equals c. Log base a of 25 equals c. Another way to say that is a to the c is equal to 25. We just took this statement and translated backwards. But we actually know what c is. C is log base a of 25. So just substituting in the value of c tells us how we can get this relationship fully fleshed out. Now that always seems like a bit of mental gymnastics. At the end of the day, these two problems here are much more easily solved by remembering that the exponential function and the matching logarithm function with the same base are inverses of each other. And if that's the case, then what we have in both these scenarios is a number, then we use the exponential, then the log, and we get back to the same number. In this case here, we start with a number, 25, then we take the log, then we use it as an exponent, and guess what? We get back to the starting value again because of that inverse relationship. With that inverse relationship in mind, take a look at this first example, log base 10 of 10,000, and think for a moment, what could the value of that expression be? It should be a nice simple number. Try for a second to work on that, and then we'll come back. All right. The most straightforward way is to make this look like the previous examples. There we had log of the same base to some power. Well, powers of 10 are fairly easily worked out. 10,000 is 10 to the power 4. And because of that inverse relationship, really the 4 is the important part here. Then we take the exponent, use it as the exponent of 10, then we go backwards with the log. We are going to end up with 4. Similarly, if we do log base 10 of 1 over 100, take a moment to think about what that could be, and then we'll come back and check. All right, by the same logic, we should be able to express this as a power. In this case, it's going to be a negative power because it's in the denominator, but otherwise it's a 2 for 10 squared is 100. And exactly the same process. The negative 2 is run through the exponential, and then through the log, we get back to negative 2 when we're done. And you can confirm that with your calculator in a couple of keystrokes. Here we formalize that inverse process into formulas. If we start with an x, use it as an exponent, then take the log, we get back to x. Or we can do it in the opposite order. We can start with x, take the log first, and then use it as an exponent. In both cases, we have an exponential and the logarithm, one inside the other. The order doesn't matter. In either case, though, we get back to what we started with because the exponential and the logarithms are inverses. Now, stepping it up a bit, what are the other rules that make logarithms interesting in their own right, separate from the exponentials? Well, if we have log of a product, we can actually separate that out into log of one plus the log of the other. And the way I remember that is multiplication inside becomes addition outside. If we have a product inside the logarithm, we get a big plus on the outside, and then the individual logarithms of the first term or first factor and second factor. There's a similar rule for division. If we have division inside, instead of adding, we subtract. Or we have a difference, whichever terminology you've learned. We have a difference outside. It's exactly the same thing, a and b in the log still, but with a minus sign connecting it. And this actually comes from an extension of this rule here. B is essentially to a negative power. And the last rule is if we have exponents, regardless of the base. So notice these bases are different. So we can't just go back to p. But what we can do is we can bring powers out front, or bring the exponent out front as a multiplier. So here we can't do all the cancellation, but we can bring that exponent in front of the log, and then we have a simpler expression in a logarithm. These rules come in surprisingly handy from time to time, and these are the kinds of things that you would be expected to both have memorized and know when to apply as part of solving an equation.